Hello and thank you for joining the lesson today. Today we're looking at upper and lower bounds with trigonometry, and it's a revision lesson. I am assuming you know about error intervals, upper and lower bounds with common measurements, finding the upper and lower bounds with measurements such as mass and distance and so forth. So we have here a question 1, that says the diagram shows a triangle PQR and the lengths of the sides are given correct to 1 decimal place. And we can see that there is an angle labelled X, and opposite this angle we have the 1.3 centimeter length, which is the opposite side, and the hypotenuse of this triangle, because it's a right angle triangle, is 6.6 centimeters. And we are asked to work out the upper bound for the value of the angle X. And to do that, we've got to work out the upper and lower bounds of each measurement of the triangle. And to do this, we would need to have an understanding that if the lengths are measured correct to 1 decimal place, then it means that the instrument used to measure the length is precise to the 0.05 centimeter. And this is because if the lengths are measured to 1 decimal place, it means that the measurements are rounded off at the 0.1 place value. And it's only by dividing 0.1 by 2 do you get 0.05 centimeters. Now the precision of each measurement would be plus or minus 0.05 centimeters. So to get the lower bound, we would have to take 0.05 from the measurement given, and to find the upper bound of that same length given, would have to add 0.05 to the measurement of that length. And we can write this as a summary with the error interval. So we have the lower bound is less than or equal to the length we measured, which is less than the upper bound. Now we'd have to work out the bounds of the opposite length and the bounds of the hypotenuse, and you can pause this video to see how that's been worked out. So now that we've obtained the bounds of the opposite side and hypotenuse, we can now think about how SOHCAHTOA can help us find the angle X. By using sine of X equals opposite of our hypotenuse, we can work out the value of the angle X. Now, the value of the angle X we're looking for that's of interest to us is the largest possible value of X, is the upper bound for the value of X. Now to have the upper bound of the value of X, we would need the upper bound of the opposite side length and the lower bound of the hypotenuse. It is because the opposite to hypotenuse ratio increases as the hypotenuse gets smaller and the opposite gets larger. So the upper bound of X occurs when X equals sine inverse of the opposite over hypotenuse yields the largest possible value of X. So we can look at examples of this. We have sine inverse of 0.5, you only get 30 degrees. But when you have sine inverse of 0.6, which is a larger number, you get 36.9. So the angle X gets larger when that ratio opposite to hypotenuse gets larger, or when that fraction opposite divided by hypotenuse is larger. So if we use the upper bound of the opposite side, which is 5.35, and we divide it by the lower bound of the hypotenuse, 6.55, we will then be able to work out X, which is sine inverse of the fraction, and X will give us 54.8 degrees to 1 decimal place. So have a go at this reasoning and literacy exercise pause this video and attempt it first, and we can go through the answers. So welcome back, and well done if you had a go at that. Have a look at the answers, and here is a question for you to try on your own. So pause this video and come back to this when you've had a go. Okay, so to find the lower bound for x, we would need to ensure that that fraction opposite over hypotenuse gives us a small value, the smallest possible value. So we would need the upper bound of the hypotenuse and the lower bound of the opposite side. So the upper bound of the hypotenuse is 6.65 and the lower bound of the opposite is 5.25. So we can work that out to get x is equal to 52.1 degrees to 1 decimal place.